Welcome to the first video for Lecture 3. The Lecture 3 topics are related to uncertainty analysis and calibration. This video will cover uncertainty analysis and the second video will cover calibration. Uncertainty analysis were built on the concept of measurement of uncertainty covered in Lecture 2, Section 3. Measurement uncertainty tells you in your reported values that there is uncertainty associated with the measurement in terms of a plus-minus value. Recognizing that measurements always come with some type of uncertainty, then what is the combined impact of those measurement uncertainties on a calculated result? The common practice is to take multiple measurements and calculate the result as well as estimate the uncertainty based on these measurement results. How do you do this? For multiple measured values, each value is associated with an uncertainty. For example, the ideal law can be used to calculate the number of moles N added to a rigid container by microbial reaction by measuring the changing pressure P. Known values in this equation are the volume V and the temperature T. R is the universal gas constant. So in this problem, the change of pressure, volume, and temperature all have uncertainties. A typical set of data of delta P, V, and T are given here. The purpose of the uncertainty analysis is to quantify the uncertainty of a calculated value using multiple measured values, each with measurement uncertainty. We can get three pieces of useful information from uncertainty analysis. First, it can quantify and report the uncertainty associated with a measured result in the form of R plus minus delta R. Second, it can help find the maximum uncertainty allowed for each measured value xi. Third, it can help identify which measured value xi is the most critical to minimize delta R. For example, in the ideal gas law example problem, do we need to measure the temperature more precisely, or the volume V, or the pressure difference delta P? There is one other type of problem that is the opposite and not covered in this course, which is with the maximum allowable uncertainty, delta R. What is the allowable uncertainty of the measurement of each variable? We can calculate two types of errors, absolute error and root sum square error. Absolute error indicates the worst case. It is calculated with maximum error added to the measurement, which is unlikely to occur in most time. The root sum square error is more practical, and we are going to discuss more in the next slides. The approach to calculate the two errors is similar. Both use Taylor series expansion. To obtain a calculated value R by two measured values x and y, delta R is its error. And the function for the two variables x and y can be written with Taylor series expansion as R plus delta R equals R plus partial R over partial x times dx plus partial R over partial y times dy plus the higher order terms. We are interested in delta R as delta R is the error for R. If we assume small dx and dy, we can neglect the higher order terms in the Taylor series expansion equation. Therefore, by extracting R from both sides, we get delta R equals partial R over partial x times dx plus partial R over partial y times dy. And this slide shows how to calculate the absolute error with two variables x and y. Absolute error epsilon equals absolute partial R over partial x times dx plus absolute of partial R over partial y times dy. In a more general case with n variables, change x and y to xi, where I is from 1 to n. In root sum square error calculation, we also use the first order term only from the Taylor series expansion. We ignore the second and higher order terms, assuming dx and dy are small. From the name of this error, we can see that it calculates by taking a square root of the sum of the squares of all the first order terms. The square terms take care of any negative values in this case. In uncertainty analysis, you take partial of equation with respect to each partial derivative of equation with respect to each measurable value. You might refer to the course packet 3-3 when you take partial differential derivatives. It's easy to make mistakes in making partial derivatives, and one quick way to check if you have done it correctly is by checking the units. The units should all match those of the original equation. Let's go back to the ideal gas law example. We want to find the uncertainty of n, the number of moles, and we need to know for each variable the typical value and uncertainty. The uncertainty information usually can be found in the spec sheet of the sensor used. In this specific problem, delta P, V, T, and R are given. This slide shows the partial derivatives for the variables with uncertainty, delta P, V, and T. Again, unit check can help to confirm that you did the derivatives correctly. By inserting the given values, we can calculate the first order terms. If we compare the three terms, we can see V and T, both with a magnitude of 10 to the power minus 5, have a much bigger impact on the final uncertainty result. Based on the previous calculations, we can find the root sum square error for n. First, square the terms up and add them together, then take the square root. In the end, we get the typical result for the ideal gas law problem. Please note how we round the numbers so that they have the same precision. Remember, uncertainty analysis can tell us three things. 1. Uncertainty of a calculated result using multiple measured values with error. 2. Which measurement contributes most to error? That indicates where to spend money to improve. Third, allowable error of each measurement. This brings us to the end of this lecture 3, section 1, where we mainly talked about uncertainty analysis. Section 2 will be about calibration. Please write down any questions you might have about these materials and ask them during our lecture time. Thank you.